Welcome to this video. In this video we will be talking about the secant method, so that by the end of this method you will be able to use this method to solve a nonlinear equation. Now the secant method is an open method like Newton's method was, and it avoids one of the drawbacks of Newton's method in that we do no longer need to calculate the analytical derivative in the secant method. So here is the general procedure. I have some function for which I want to find the intersection with the x-axis, meaning finding the root. And I'm going to start the secant method by two initial guesses, 2 points, x naught, and to indicate that there is a second point that I need before x naught, I'm going to give this the superscript x negative 1. So those two initial guesses should be close to a root. So this, let's say here is my x negative 1, and my next initial guess is this x naught over here. Now the procedure does this. It tries to find the intersection of the line that goes through the function values of these 2 points with the x-axis, and that intersection will be my new solution estimate x1. So let's do this. I'm going to have my point x negative 1. I'm going to evaluate the function at that point. I have my point x naught. I'm going to evaluate the function there. And then I'm going to draw the line through those 2 function values, and I'm going to find the intersection with the x-axis, and that will be my new solution estimate x1. Now, what is the slope of this line that I drew? Well, there's 2 ways of calculating it, right? The slope is always a delta y over a delta x. So the delta y here, if I look at the right part of this graph here, is the delta y would be the f of x negative 1 minus the f of x naught divided by the delta x, which would be x negative 1 minus x naught. But that slope can also be calculated on this right part, on this left part here, which would be the delta y would be f of x naught minus the intersection with the x-axis, so 0, divided by a delta x, which would be x naught minus x1. So now I know all of these quantities in this equation except for the new solution estimate that I want to find. So let me solve this equation for x1. Just multiply by this denominator here, so I get x naught minus x1 is equal to f of x naught. And I'm going to bring the rest over. So that's x negative 1 minus x naught divided by f of x negative 1 minus f of x naught. So now I'm going to bring the x1 over to one side, and that gives me then x1 is equal to x naught minus this entire right-hand side. Okay, that will then be the formula to find my new solution estimate that I'm then going to use with the next update formula. So my new solution estimate is x1, and I still need the prior solution estimate which is then my x naught to calculate an x2. And I'm going to keep on doing this until, well, either the tolerance in function or the estimated relative error is below an acceptable value. So let's write the general update formula in here. So I'm going to derive this formula by setting just I equal to 0, which means my new value xi plus 1 is equal to my prior value xi minus f of this prior value, so f of xi, divided by f of my prior value, so f of xi minus 1 minus f of my prior value minus f of xi times my prior x value, so xi minus 1 minus my prior x value xi. That is then the general update formula for the secant method. Okay. Now how does this secant method compare to Newton's method? Because there's some similarity, right? Because in secant method and in Newton's method, we find our new solution estimate by finding the intersection of a line with the x-axis. So here is Newton's method again, and let's compare the two. Here is secant's method. Let me take that first part over here, and let me recast this a little bit. I'm going to keep in the numerator the f of xi. but I'm going to move that additional x term here that is after the fraction, I'm going to move that into the denominator. So in the denominator, I have f of xi minus 1 minus f of xi divided by xi minus 1 minus xi. So now everything in these two formulas is the same except for the denominator. In the Newton's method, there is the analytical derivative f prime evaluated at xi, and in the secant method, there is this fraction. Now, if you remember from calculus, what is the definition of the derivative? Well, it turns out the definition of the derivative, the analytical derivative f prime, is exactly what's written here in the secant method in the limit of the 2 points coming infinitely close to each other. So in the limit of xi minus 1 going to xi, this denominator term of the secant method is equal to the analytical derivative. So this method is the same as Newton if xi minus 1 converges to xi, which is what it's supposed to happen if we get closer and closer to the true solution, because then these individual solution estimates are supposed to converge to the true solution. Now, the big advantage of the secant method is that it does not require the calculation of this analytical derivative. There are some problems with this, though. The convergence of the method depends strongly on the choice of the initial two starting points. And those then have to be derived again from some physical insight into the nonlinear equation that we are trying to solve. So let's do an example again. We're trying to find the root of f of xi equal to x squared minus 1 using two initial guesses, 3 and 2. Okay, so let's dive into iteration 1 already. So iteration number 1, which is when I is equal to 0. So let me write this formula out here. So I'm just going to take this general update formula and plug in I equal to 0. So I get x1 is equal to x naught minus f of x naught divided by f of x1 prior, so x negative 1, minus f of x naught times x of negative 1 minus x of naught. Okay? So let's identify the values that we need. We have an x negative 1 that is 3, so that goes into here and here. And we have a value of x naught that is 2, that goes into here, here, and here. Okay, so I will need to know what is f of x negative 1. So that's f of 3. It's 3 squared minus 1, that is 8. And I will need to know what is f of 2. So f of x naught, that's f of 2. That's 2 squared minus 1, that's equal to 3. Okay, so let's plug these values in. There's one more x naught over here. So 2 minus f of x naught, that is 3, divided by f of x negative 1, that was the 8, minus f of x naught is 3, times x negative 1, 3, minus x naught, 2. So that's 2 minus 3/5 times 1. So that is equal to 10/5 minus 3/5 is equal to 7/5. That is equal to my x1. So my x1, my new estimate, is equal to 7/5. Okay. Iteration number 2. Let's do one more. Number 2. So I is equal to 1, which means my update formula is simply x2 is equal to x1 minus f of x1 divided by f of x0 minus f of x1. I'm just advancing the index I by 1 times x0 minus x1. Okay, let's plug in the values that I know. Let me mark some of them here. I know the x0 value. Right, forgot to close the parentheses there. That's where the x0 goes. And my x1 goes into here. Okay, so now I need to know what is f of x1. So f1 was 7/5, so that's 7/5 squared minus 1. It's 49 over 25 minus 25 over 25. That's equal to 24/25. That's my f of x1. And let's plug the rest of the values into the formula here. So we got 7/5 minus f of x1 was the 24 over 25 divided by f of x0. F of x0 was over here, so that's my 3. 3 minus f of x1, that was 24 over 25. And this times x0, that was 2, minus x1, that was my 7/5. Okay, so if you plug all of these values in, you will find that x2 is equal to 285 divided by 255, or 1.1176470, and so on. Okay, that would be the answer after 2 iterations. And now we would have to look at the tolerance in function, whether that is acceptable, or the estimated relative error, whether that is acceptable to make the decision of whether we are going to continue on, or whether our current solution estimate of this 285 over 255 is good enough. And that's how you apply the secant method. Thank you for watching.